Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 5th, 2026, just 2 days ago. It introduces a method called output embedding centering, which stabilizes large language model pre-training by anchoring output embeddings to the origin, thereby fixing the root cause of logic divergence rather than just treating the symptoms. The paper is titled Output Embedding Centering for Stable LLM Pre-Training. And as we'll see later, the results demonstrate that this approach is significantly more robust to hyperparameter changes than current standard techniques. Figure 1 illustrates the core geometric concepts behind the proposed method. The left panel plots the z loss function, showing how it penalizes deviations where the partition function z differs from 1, effectively keeping logit sums in check. Then the center panel visualizes the actual problem. The red dots show how output embeddings naturally drift away from the origin during training, creating a cluster with a non-zero mean vector, mu. The green dots demonstrate the effect of mu centering, which shifts this cluster back to the origin to restore symmetry. Finally, the right panel confirms this with empirical data, displaying a histogram of dot products that satisfy the theoretical bounds required for stability. Table 1 summarizes exactly how each approach tackles instability. The top row shows the standard z-loss. While it handles positive divergence well, notice that for negative divergence, it only enforces a collective constraint. Moving to the next rows, both mu-loss and mu-centering go a step further. They suppress single divergence in both directions. Since controlling single logits is stricter than controlling them collectively, this theoretical advantage allows the new methods to prevent divergence where z-loss fails. Alright. Figure 2 now confirms these theoretical advantages with empirical data. The top panel shows the training loss as we increase the learning rate along the x-axis. You can see that the baseline in red and z-loss in blue shoot up dramatically on the right, indicating divergence. However, the mu-loss and mu-centering lines in orange and green stay flat, proving they handle high learning rates without instability. Then, the bottom panel quantifies this by plotting learning rate sensitivity against model size. Consistently, the proposed methods remain at the bottom of the chart, meaning they are much less sensitive to configuration changes than the baseline or z-loss. So, while the previous figure visualized the trends, Table 2 lists the specific numbers for performance and efficiency. In the first section, looking at optimal loss, we see that for every model size, the final performance is virtually identical across all methods, meaning stability does not come at the cost of quality. The second section highlights the real difference. For learning rate sensitivity, the proposed mu-loss and mu-centering consistently achieve much lower scores than the baseline or z-loss, confirming they are far more stable. Finally, the bottom section covers training cost. While z-loss adds up to 6% overhead for smaller models, the new methods are incredibly efficient, adding less than 1% to the total training time. Well, having seen the performance gains, Figure 3 reveals the internal mechanics driving that stability. The top left panel plots the average logit value. Notice how mu-centering holds it perfectly at 0, while z-loss forces it negative and the baseline just explodes. Crucially, the bottom left panel tracks the mean embedding norm, or how far the embeddings drift from the center. Here, we see that z-loss fails to stop this drift at high learning rates, behaving almost like the baseline. In contrast, the new methods keep the norm flat, which, as shown in the bottom right, prevents the maximum logit values from spiking uncontrollably. Okay, following the mechanics, Table 3 examines how sensitive these methods are to the regularization hyperparameter, lambda. The table splits the results, with mu-loss on the left and z-loss on the right. If you look at the learning rate sensitivity section for mu-loss, the values stay consistently low and stable, regardless of whether lambda is 10 to the minus 4 or 100. However, z-loss on the right is much more fragile. In the last column, setting lambda to 100 causes the sensitivity score to spike above 1.0, showing that z-loss fails if the hyperparameters are not tuned exactly right. Wrapping up, the main takeaway is clear. Output logit divergence is fundamentally a geometric issue caused by embedding drift. By centering these embeddings, the proposed method fixes the root cause rather than just the symptoms, enabling stable training at high learning rates with negligible computational cost. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.